Finally, I'm getting over an amp out and the power transistor isn't burning my finger. Hi, I'm Kevin. Welcome to my cave. Last time in this series, we were looking at a textbook current source, the Howland current pump, which was the first one that we examined that could both source and sink current. We found that it had a few problems. The input impedance was horribly low, the voltage compliance was poor, and the output impedance was both low and variable. It could even be negative. A smaller load resistance in some cases could see a smaller current. Now I want to fix all those problems. By the end of this episode, we should have built a circuit that has the insanely high input impedance of an op-amp, voltage compliance nearly to the power rails, and an extremely high output impedance. Recall that in a current source, high output impedance is desirable. The improvement is often attributed to the legendary analog designer Bob Widlar. It's not the Widlar current source, also named for him, which is a deliberately unbalanced current mirror that we saw over in Transistors 101. But it's another great circuit from a brilliant and eccentric designer. Let's start with the Howland current pump from last time. A lot of our trouble came from the fact that the resistor that provides voltage feedback on the input side is also the resistor that senses the current. To get a decent amount of current out, the resistor has to be small, but since the ratio of R3 and R4 is critical, R3 will also have to be small, and whatever is driving our current source will have to be able to source a significant fraction of the output current. So let's go at this a different way. We'll add a separate resistor for current sensing, which we can make almost arbitrarily small. Obviously, we'll take the load from the other end of that resistor. We'll put that resistor inside the feedback loop, so feedback will compensate for its voltage drop. So what does this mean for what the circuit does? Well, let's make a few simplifying assumptions. We'll assume that the feedback resistor R4 has a value much larger than the sense resistor R sub S, so that we can work as if the feedback loop draws no current from the sense resistor. I'll come back to this later. We'll also assume that the ratio between the values of the upper pair of resistors matches the ratio between the values of the lower pair. We made this assumption with the Howland current source as well, and it turned out to be a problem. But we'll see in a little bit that we now have a better way to solve it in this circuit. It'll be more convenient to write the equation governing the resistor ratios as a couple of linear equations. Let's label the voltages at the two ends of the sense resistor, V1 and V2. Since we're ignoring the tiny current flowing in R4, the output current can be found by applying Ohm's law to the sense resistor. We can find what it is if we can calculate the voltage difference between the voltages V1 and V2. That's not too hard. The pair of resistors R1 and R2 is a voltage divider, since we assume as usual that op-amp inputs draw no current. We have an expression for the voltage at the inverting input of the op-amp. Similarly, the pair R3 and R4 are a voltage divider, and we can write down the expression for the voltage at the non-inverting input. The op-amp golden rules tell us that in the presence of negative feedback, the op-amp will make these two voltages equal. We can substitute in the scaling factors for R2 and R4. Then we can factor the numerators and denominators, multiply both sides by 1 plus a, and cancel common factors of R3 and R1. Rearranging the terms that remain gives us the voltage difference that we wanted, which gives us the formula for the output current as a function of the input voltage. It's still linear. The next problem that I want to tackle is the ratio mismatch on the two voltage dividers. We saw with the Howland pump that our 1% resistors weren't good enough, and ratio-matched resistor networks can be a bit pricey. But when we look at this part of the circuit, it's a classic op-amp difference amplifier, just like the one we saw in an earlier episode. We can get this subcircuit in a single IC. Please indulge me for a brief interruption. As longtime viewers of this channel know, it's always free to all comers. Nothing is ever paywalled. But I do make one request of my viewers, that you take care of one another. To that end, all my ad revenue goes to charity. The current featured charity is World Central Kitchen. It has a sole mission: bring freshly prepared meals to those living in the wake of a natural disaster, a man-made emergency, or a humanitarian crisis. It is a team of food first responders, mobilizing swiftly to get meals to the people who need them most. Its model of swift action in time of need, leveraging local resources and adapting in real time, reflects a belief that a nourishing meal in a crisis is much more than a plate of food. It's hope, it's dignity, and it's a sign that someone cares. At the time of filming, World Central Kitchen has served over 600 million meals in communities all over the world. I know that Kevin's Cave people are a generous lot who believe in taking care of others. Won't you help out today, using the link up here or down there, or at any rate somewhere nearby? Thanks so much for your generosity. And now back to the video. There's a whole zoo of packaged diff amp ICs available. I'm going to use the INA143, which is reasonably inexpensive, certainly cheaper than a low offset op amp plus a pair of high precision dividers. You can see on the data sheet that the op amp plus 4 resistors is exactly what we drew. The specs are close to what we need. It's got a reasonably low offset voltage. 100 microvolts typical, 250 microvolts max. The gain error, or equivalently the ratio mismatch between the resistors, is also pretty good. It's 0.01% typical and 0.05% max. It's not important for this circuit, but we do have to notice that the internal resistors are trimmed to have the correct ratio, but not trimmed in absolute value. So why didn't we use this before for the Howland current pump? The problem there is that the output of the Howland circuit is tied directly to the non-inverting input of the op amp. That node isn't broken out in the INA143, and in fact I've never seen a packaged diff amp that gives access to it. So using a packaged amp just wasn't an option for the Howland circuit. The chief problem for this circuit is that its input impedance is relatively low, just 20K differential and 55K common mode. That's not acceptable. We'll deal with the low input impedance using the same brute force technique that we used last time. Put an op amp buffer on the input. Let's go to the cave and test what we have so far. As usual, the schematics are on the project GitHub, link in the video description. And as usual, I'm building and testing in stages. First up is just the voltage divider that I'm using to produce the input voltage. And it looks good, ranging a little farther than plus or minus 6 volts. Now I've added the input buffer using half of a TL072 dual op amp. The unused half is wired according to good practice as a unity gain buffer with its input grounded. The output voltage still ranges over a little more than plus or minus 6 volts. I'll take it. I've added the diff amp. It's wired backward for a gain of 0.1, and the load resistor is 100 ohms, so I expect an output of a milliamp for each volt of the input. The input voltage is on the blue meter and the output current is on the yellow meter. The only load impedance is the current shunt in the meter. I power it on and vary the input voltage and it seems to be tracking. So far, so good. Let's see how it performs with a 1K load resistor. The Howland pump struggled to maintain voltage compliance with that high a load impedance. This circuit is handling it with ease. What if we want to regulate a tiny current? I'll increase the sense resistor to 10K so that we should see 10 microamps out for every volt in. I'll try adjusting the input voltage again. The general trend is right, but the currents are way off. The problem, of course, is that we had worked under the assumption that the feedback resistor had a value much greater than that of the sense resistor. And then we violated that assumption by making the sense resistor too large. Fortunately, the problem has a simple fix. We put a unity gain buffer in the feedback loop. Now R4 can't steal current from the load. This solution even comes at approximately zero cost. Dual op-amps are no more expensive than the corresponding single ones. In fact, they're often cheaper. Go figure. Let's try this change out in the cave. I've added the buffer just by running a pair of DuPont wires back to the other half of the dual op-amp that buffers the input. The circuit seems to be tracking correctly now, at 10 microamps per volt. What about high currents instead? I've put in a short circuit for the load and swapped the sense resistor for a 10 ohm one for an output current range of plus or minus 60 milliamps. It works up to a point. The diff amp is limiting the output current to positive 28 and negative 22 milliamps. It can't drive a higher current than that. I've decided to up the current handling in the lazy man's way. I've put in a pre-packaged unity gain amp capable of handling a higher current. I'm using an LT1010, whose bond wires are rated for 150 milliamps. But I'm breadboarding with the 1 in the 8-pin dip, so I have to watch out not to have it dissipate more than about half a watt. The LT1010 is on the board here, and now I'm using a 3.3 ohm load, 3 10 ohm power resistors in parallel. The 100 ohm sense resistor will give us the same plus or minus 6 milliamp output that we had before. But now we can try to put the 10 ohm resistor back in and see if we can get the plus or minus 60 milliamps. Unfortunately, I lost the video. The numbers on the meters looked good. But the thermal camera shows that we are pushing things close to the limit. The case of the chip is at about 6 degrees Celsius. We will be dropping nearly the full 12 volts through it at 60 milliamps. That's 720 milliwatts. The datasheet says that the thermal resistance, junction to case, is 45 Kelvin per watt, so the junction will be about 33 Kelvin higher than the case, or 93 Celsius. That's actually still within the safe operating area, but I hate running stuff hot enough to burn my fingers. So what can we do to get more current? Well, the LT1010 datasheet has a clever idea for increasing the output drive capability. I'm going to save the detailed discussion for another episode, and just make the modification here. It's just a couple of power transistors and a handful of resistors, but in a fairly unusual configuration. Of course, we have to do the thermal calculation on those power transistors. And in this case, the voltage drop, the current, the power dissipation, the temperature are all the same as the ones we used in the last episode, so I know we're in a safe region. Treating this new circuit as a black box, let's build it on the breadboard and give it a try. I've got it here on the breadboard with the 10 ohm sense resistor again. And it's doing the plus or minus 60 milliamps without breathing hard. Now I'm going to change the resistor to half an ohm, two 1 ohm 3 watt resistors in parallel. I should get 200 milliamps out for every volt I put in. Just as last time, I'm running my desk fan over the circuit, because my heat sinks are pretty wimpy. You can see one heat sink fluttering in the breeze. We should be set up to try some real current here. The output current is tracking the input voltage all the way out to plus or minus 1.2 amps. Electrically, it's looking good. Let's make sure it's also okay thermally. With the current at 1.2 amps, the power transistor that's driving the output stays reasonably cool, below 50 Celsius. If I twist the knob to drive 1.2 amps in the opposite direction, that transistor cools down while the other one heats up. Let me jump forward in time a couple or 3 minutes. Once things settle down, the current active transistor reaches about the same 50 Celsius. The highest temperature that the camera sees is on the power resistors, and they're still comfortable to have a finger on. So is the hot transistor. The finger touch thermometer agrees with the camera. We've now fixed all the problems that I was promising to fix. The current source can handle over an amp, and with proper heat sinking, we could at least triple that still using the same parts. It can both source and sink current, and drive any load from a short circuit up to a reasonably high compliance limit. This is, then, a good time to break off our deep dive into voltage-controlled current sources. We could make further improvements, going to higher output voltages, greater speed, greater precision, and so on, but you have most of the basic ideas. I may do variations on the theme if I have projects that call for them. In fact, we've examined a nearly complete set of the bread-and-butter negative feedback circuits that designers work with every day. Next time, I want to do a quick explanation of what's going on with our 2-transistor output circuit. I found it rather clever, and it's a significant improvement over the basic 2-transistor push-pull follower. In the episode after that, I'm going to take a break from negative feedback and look at a few circuits where we actually want positive feedback instead. I hope you'll stay tuned for those, and perhaps offer the YouTube algorithm some sort of suggestion that you want to see them. Until then, stay safe, stay healthy, stay curious, and please take care of one another. Bye!